This video we are studied about factors influencing carbonyl frequencies. All the carbonyl compounds observed in the region 1762 1665 centimeter inverse due to the searching vibration of carbonyl bond. The distinctive carbonyl band is particularly useful for diagnostic purposes because of it has characteristics high intensity and few other functional groups observed in this region. Different carbonyl compounds observed in the narrow range within general carbonyl region. The exact wave number of carbonyl stretching frequency can give you clues as whether the compound is aldehyde, ketone, carboxylic acid, esters, amide, acyl halide, and acetic anhydride. Factors influencing the carbonyl stretching frequency, such as physical state of measurement, electronic effects. The electronic effects are inductive effect, mesomeric effect, and field effect. Hydrogen bonding, bond angle. First one, physical state of measurement. The carbonyl stretching frequency of neat sample of a saturated aliphatic ketone observed at 1715 centimeter inverse. Example, acetone, cyclohexanone, etc. The absorption frequency observed for a neat sample is increased in nonpolar solvents. See the structure. The first structure is neutral molecule of ketone. The second structure is polar canonical structure. Polar canonical structure means the completely transfer of pi electron to the oxygen atom because of oxygen is electronegative atom. So therefore carbon get positive charge, oxygen get negative charge. The third structure is resonance hybridized structure. This is not completely transfer of electron. In this case, the electron clouds are moved towards the oxygen. The oxygen get partially negative charge and carbon get partially positive charge. This is the resonance hybrid structure. In a solution of nonpolar solvents, the molecules are separated to each other. Therefore, the contribution of neutral structure 1 to the resonance hybrid structure 3 increases. The carbonyl bond strength increases and carbonyl such a frequency to a higher wavelength. Polar solvents reduce the frequency of absorption. This is due to increasing contribution of polar canonical structure 2 to the resonance hybrid structure 3. The carbonyl bond strength is decreases. The carbonyl frequency shift to a lower wave number. The hydroxylic solvents reduce the frequency of absorption. For example, carbonyl searching frequency of acetone in 10% of methanol is observed at 1706 centimeter inverse. This is due to formation of intermolecular hydrogen bonding between solvent and ketone. Here, methanol molecules of carbon monoxide bond strength is decreases and carbonyl searching frequency shift to a lower wavelength. See the structure. The third structure is resonance hybrid structure, and this fourth structure is resonance hybrid structure of oxygen is intermolecular hydrogen bonding between acetic acid. The acetic acid containing H plus ion is hydrogen bonded with acetone containing oxygen atom. Therefore, when we are using the acidic reagent, the carbonyl searching frequency will decreases. In other case, a specific example of benzamide and phenylacetate. As a nitrogen atom is less electronegative atom compared with oxygen. Because of oxygen is the second most electronegative atom, nitrogen is third most electronegative atom. In amide is more labile and participate the greater extent in conjugation. The presence of greater degree of conjugation of carbonyl absorption frequency is relatively lesser than in esters. The benzamide absorbed carbonyl frequency at 1693 centimeter inverse. The phenyl acetate absorbed the carbonyl searching frequency 1730 centimeter inverse. In most of the cases, mesomeric effect works along with the inductive effect and cannot be ignored. The important note that only inductive effect is considered when the compound is meta-substituted. In para-substitution, both inductive and mesomeric effect become important, and the domination of one over the other will decide the wave number of the absorption. See the structure. Para-amino acetophenone absorbed at 1677 centimeter inverse. Para-nitroacetophenone absorbed at 1700 centimeter inverse. Para-methoxyacetophenone absorbed at 1684 centimeter inverse. Phenyl acetate absorbed at 1770 centimeter inverse. The first one, para-amino acetophenone. In general, the nitrogen is a good electron donor in presence of amino group. Generally, amino groups are electron donating group. Therefore, the amino group donates the electron to the benzene ring involved in resonance. The carbonyl bond order is decreases. When the carbonyl bond order decreases, carbonyl bond strength also decreases. Therefore, carbonyl searching frequency decreases. Next one, para-nitroacetophenone. The nitro groups are electron withdrawing group. Therefore, the electron density moves towards the nitro group. The carbonyl bond order is increases. When the carbonyl bond order increases, carbonyl searching frequency also increases. Next one, para-methoxyacetophenone. The methoxy group containing oxygen donate the lone pair of electron to the phenyl ring. The carbonyl bond order is decreases. When the carbonyl bond order decreases, the carbonyl searching frequency also decreases. Next one, phenyl acetate. In the phenyl acetate group containing carbonyl compound, NAD does not directly bonded with the phenyl ring. It is bonded with the electronegative oxygen atom. So the oxygen atom donates the electron to the phenyl ring. The carbonyl bond order highly increases. Therefore, carbonyl searching frequency also increases in phenyl acetate. In the above examples, due to low electronegativity of nitrogen atom, lone pair of electrons participate more in conjugation in compound 1 as compared to the compound 3. Thus, in compound 1, carbonyl searching frequency absorption occurs at lower wave number compared to the compound 3. In compound 2 and compound 4, inductive effect dominates over the mesomeric effect, and hence absorption takes place at comparatively higher frequencies. Hydrogen bonding. The presence of hydrogen bonding changes in the position of shape of an infrared absorption band. Frequencies of the both stretching as well as bending vibrations are changed because of hydrogen bonding. There are two types of hydrogen bonding. One is intramolecular hydrogen bonding, another one intermolecular hydrogen bonding can be differentiated by the use of infrared spectroscopy. The intermolecular hydrogen bonding involves association of two or more molecules of the same or different compound, and it may result in dimer molecules in carboxylic acid. The intramolecular hydrogen bonds are formed when the proton is donor and acceptor are present in the single molecule under special conditions that allow required overlap of orbitals. Example, formation of 5 or 6 member rings. The extent of intermolecular hydrogen bonding depends upon the concentration of the solution, and hence the position of the shape of the absorption band also depends on the concentration of solution. See the first structure. The concentrated solution of 2 mole of primary alcohol The two mole of primary alcohol, one alcohol oxygen atom interacted with another alcohol hydrogen atom to formation of intermolecular hydrogen bonding. When the intermolecular hydrogen bonding OH observed at 3550 to 3200 centimeter inverse because of lower wavelength compared with free OH group. The free alcohol containing OH searching frequency observed at 3650 to 3590 centimeter inverse. The more concentrated the solution, the more likely it is for the OH containing molecules to form intermolecular hydrogen bonds. It is easier to stretch than OH bond if the hydrogen bonded because of hydrogen is attracted oxygen neighboring molecule. Therefore, the OH stretching frequency of alcohol observed at 3550 centimeter inverse, whereas the OH stretching frequency band of in dilute solution appears at 3650 centimeter inverse. Additionally, the hydrogen bonded OH groups also have broader absorption bands, whereas the absorption bands of non hydrogen bonded OH groups are sharper. Thank you.